Welcome all to the part B. Now that we know how to characterize data, we move to measure relationships. This section focuses on similarity and dissimilarity. In question 5, we'll examine how to calculate distance for different type of attributes, whether it's simple mismatches for nominal data or the Jaccard distance for asymmetric binary data like workshop attendance. We'll apply these concepts in question 6 and question 8 to compare student profiles using multiple matrices, Euclidean, Manhattan, Minkowski, and supremium distance. We will also look at question 7, which introduce advanced methods like streaming algorithms to approximate medians in massive datasets with where standard sorting is too slow. Let us see how we classify the difference between two students. Hello everyone. Welcome back to part B of internal assessment 1, similarity and dissimilarity in feedback data. So let's now discuss how to compute dissimilarity between student feedback profiles where the attributes belong to different data types. Each type requires a different method. First, nominate attributes. Sorry, nominal attributes. Nominal attributes are labels without any ordering, such as department or elective chosen. To measure dissimilarity here, we simply count mismatches. If two students share the same category, the dissimilarity is 0. If they differ, the dissimilarity is 1. It's very simple. For multiple attributes, the overall dissimilarity is the number of mismatches divided by the total number of attributes. Second, asymmetric binary attributes. These are yes or no variables where yes is more meaningful than no. For example, attending a workshop. Here we use the Jaccard distance, which only considered positions where at least one student has a yes. We count M11. In this case, both say yes. M01 first say no and second says yes. And M10 first says yes and second says no. We ignore M00 where both say no. This gives us an accurate measure different with a measure of difference without letting meaningless no matches reduce the distance artificially. Third is numeric attributes. Example includes CGPA or the attendance percentage in our college day-to-days. Here we first normalize the data so that the attribute with large scale do not dominate. After normalization, we compute distance using the methods such as Euclidean or Manhattan. So just a minute. Yeah. So numeric attributes, yeah, it is. So the third one is we have done. Now coming up on the fourth, which is term frequency vectors. These come from the text feedback where each student is represented by the count of keywords. Because such vectors are sparse and high dimensional, Euclidean distance performs poorly. So instead of that, we use cosine dissimilarity. We compute cosine similarly using the angle between the vectors and then convert it into dissimilarity by subtracting from 1. A value close to 0 means student expresses similar topics. A value close to 1 means their feedback was very different. So now coming upon the question 6, which is distance measures between two students' interaction profiles. In this question, we compare two student-faculty interaction profiles represented as four attributes pair, which is P1 is equals to 22, 1, 42, and 10, and P2 is 20, 0, 36, and 8. These attributes represent mentoring hours, project review attended, assignment submitted, and the infrastructure used respectively. So here we compute four distance measures as follows. First one is Euclidean distance. Subtract each pair, square the difference, sum them, and take the square root. This gives the straight line distance. Second one is Manhattan distance. Take the absolute difference of each pair and sum them. This measures the total blockwise distance. Third one is Minkowski distance with h is equals to 3. Raise each absolute distance to the power of 3, sum them, and take the cube. Cube root. This aggregates larger difference more strongly. Fourth one is supreme distance. Fourth one, here we get the supreme distance, the maximum absolute difference across all attributes. The single largest difference becomes the difference. These distance help us determine how similar or different the two students' engagement patterns are. Now coming upon the question 7, which is median approximation in massive student feedback datasets. So in this question, we discuss the methods for approximating the median when working with massive student feedback datasets. Computing the exact median requires sorting all data, which is O and log n time, and high memory usage. For very large datasets, this becomes inefficient. So we use faster approximation techniques. First one is binning, which is histogram-based approximation. Divide the data into bins, that is 1 to 5, 6 to 10, and so on. Build the histogram in one pass, find the bin containing n by 2, and interpolate using the group data median formula, and it runs in the linear line. Second one is random sampling. Take a small sample that is a few thousand points, sort only the sample, and compute its mean. This sample is also very close to the true median. Sorting cost depends only on the sample size. Third one is streaming algorithms. Algorithms like T-Digits or the Greenwald Khanna makes one pass through the data and maintain a compact summary. They allow querying any quantile, including the median, with guaranteed error bounds. These are ideal when the data doesn't fit in the memory. So, in summary, these methods gives highly accurate median approximations with far lower time and memory requirements than exact computations. So now let's move forward with our final question of part B, which is question 8. Here it is student faculty similarity analysis using multiple distance measures. So in this question, we compute a new feedback quantity vector S is equals to 1.4, 1.6, representing faculty responsiveness and infrastructure support with five existing profiles, which are S1 is equals to 1.5, 1.7, S2 is equals to 2.0, 1.9, S3 is equals to 1.6, 1.8, S4 is equals to 1.2, 1.55, and S5 is equals to 1.5, 1.8. So coming up on part A, ranking using four measures. Yeah. So first one is Euclidean distance. Smaller is more smaller, which says. Second one is Manhattan distance, which is sum of absolute differences. Third one is supreme distances, which is maximum absolute difference. Rankings are S1 first, then S2 and S1 first, S3 and S4 tied, then S2 and S5. Cosine similarity is closer to 1 is more similar. And here the ranking is S1, S3, S4, S2, and S5. So coming upon its part B, which is normalizing to unit length, where all vectors are normalized to unit length. sorry, yeah, where all vectors are normalized to unit length, magnitude difference are removed. In this case, Euclidean distance become mathematically equivalent to cosine dissimilarity. Thus, the ranking exactly matches the cosine similarity order, which was S1, S3, S4, S2, and S5. This analysis helps us retrieve the most relevant past feedback profiles that matches the new query. And here we can see all the calculations of the above mentioned methods in the stepwise step column. Here we have Euclidean distance, which is L2, Manhattan distance L1, supreme distance L infinite, and cosine similarity here we have. And now coming upon the calculations of part B, which is normalized Euclidean distance, we have its concept and the rankings as we have discussed. So in the next video, we'll be discussing the part C. Till then, good day. And that wraps up the part B. We have covered the essential techniques for determining how similar or dissimilar two data points are. We saw the cosine similarity is the gap go to standard for text vector because it ignores magnitude and focuses on the orientation, unlike Euclidean distance. We also ranked student profiles against a query and proved that normalizing data to unit length can make Euclidean and cosine ranging identical. So these concepts are the building blocks of recommendation systems and cluster algorithms. So make sure to understand when to use Jaccard versus Hamming, which is a mismatch for the exam. Great job following along with me. Keep practicing these calculations.